All right, so it's 7. I'm going to start recording. So I'm going to start going over some of the beginning stuff. We're going to be talking about work right now, and then I'm going to give a few more minutes to see if a few more others are going to join. So let's go ahead and get started talking about work. The first one is work. So we're talking about the applications of the things that we've been learning so far in this class. And if you've taken a Physics 1 class, you might be familiar with, if we've got a constant force, the definition of work is this W equals FD, where W is the work, F is the force, and D is the distance traveled. But like a lot of things in this class, we're not working with constants. So let's say we've got the force as some kind of equation, right? We've got this f of x type of thing going on. So non-constant force this is our force equation. And so what we can do, like always, is start by kind of having an approximation. And having this approximation can help us get closer and closer to the real answer. And eventually we can kind of see when calculus really takes over. So if we've got this non-constant force and we wanted to find the work, what we could do is approximate it with squares, right? And we can say that like Wi, some segment, this work, is the force at this xi, and then the change of that x to the next, like xi plus 1. Right? So now you can kind of see if we make these xi smaller and smaller, delta x becomes smaller and smaller, and it becomes our dx. So our delta x turns into our dx. So this guy turns into our integral here from a to b, our f of x dx, right? So it looks like a pretty simple integral. I think this is the easiest of the applications. So let's go ahead and start looking at number 1. So I'm going to go ahead and draw a spring. We're going to put a box end of it. And we're going to say that this spring has a natural length, so a natural length of 20 centimeters. Right? So now, if I tell you that it takes 40 newtons to hold that spring, and we're going to be holding it at 30 centimeters, that's a condition that we can have to find our parameter k, and you're going to see that in just a second. So now the question is, what is the work? So work from moving the spring, or this box here, from 35 centimeters to 38 centimeters. So go ahead and take a few minutes, and then we'll start working on it. So if you forget the beginning of the section talks about books, so need to refresh, look at that. I'll talk about it in just a second. Okay, so we know about Hooke's law, and this is basically saying that f of x is going to be equal to some parameter k times x, the displacement, right? What we know from the problem is that the force is 40 newtons, and this has to be equal to k times this 30 centimeters. Now, I should actually back up here and write the units in because it's important, because we've got k. So this is multiplied by 30 centimeters, right? I'm sorry, it's, there we go. It's 10 centimeters, right? Because it's the displacement. And we're going from 20 to 30. Now, this centimeters makes a big difference because we're not looking in terms of centimeters in the long run. Our units are going to be using meters. So what we really need is k times 0.1 meters. Now this leads us to k being 400, right? Now we can go ahead and start looking at our work done. So our work is this integral. Now we'll talk about the bounds in a second. But we have 400 x dx, right? Now the bounds, again, we have to be talking about meters, and we have to talk about the displacement, right? So even though we're going from 35 to 38 centimeters, we're looking at a displacement of 0.15, 0.18, right? Because we started at 20 and we needed to go to 35, right? So that's 15 away, and we have to be talking about meters, so it's 0.15. Similar for the top bound with 0.18, right? So now we can do this integral. This is 200 x squared from 0.15 to 0.18. We plug this in, we get 1.98 joules. So that's the work required to move this spring 35 centimeters to 38 centimeters. All right, so I think this one's a pretty straightforward application. The next guy that we're going to be talking about is hydrostatics. And the book calls it hydrostatic pressure, so we'll go ahead and call it that. So the problem that we're going to be looking at now is we've got some water. Maybe I'll draw in blue, but let me draw the shape first. So we've got some kind of triangle that's underwater. Right, something like that. And then here's the surface of the water. That's terrible water for me. There we go. And now let's do the measurements of the shape. So up above, this is 6 meters, and it goes down to a depth of 4 meters. So what is this plate feeling? How much pressure, how much force is on this plate? So first, let's set up our axes. If we actually take the x direction to be down, so what I'm going to do is place the x axis right here in the middle and go downward. This is my x direction, and it's going to be the positive x direction, right? So let me draw my shape again over here. Now what I want to be doing, actually let me draw a little bit larger because we're going to have to draw some other things on this. So what we can do, again, is type of this approximations, right? So a good approximation is to use these little rectangles over these segments of this triangle. Draw a little rectangle. Let's try to get close to one. Okay, so now if we make these really, really small, we don't have to worry about the height too much. But what we do need to care about is its position on this triangle, right? So the distance from the bottom to the midsection of this rectangle is 4. Still have my shape thing on. Is 4 meters, or sorry, 4 minus this x. I'm going to call it xi because it's this segment, right? Now, the distance from the top of the triangle to this segment is simply just xi. Now, we have to figure out what is the width of this rectangle. Well, if we draw a line down the center of this guy, we know that this right here, this is 3 meters, right? So we can try to use similar triangles to figure out exactly the width of this rectangle. We're going to call that A, right? So this line right here is A. And if we go over here, instead of our symbol of triangles, we've got that 3/4 equals A over 4 minus xi, right? This leads us to the fact that A is equal to 3 minus 3/4 xi, right? And we're going to use this later on. So what we do know about this little segment here, this rectangle, is that the pressure, so we're going to call this Pi, is equal to the density, the force, or the acceleration due to gravity, and this d, right? So the amount that we're looking at here. Now this d is basically this delta x, right? But what we can do is we know that the force, so I'm going to say Fi here, the force on this little segment is rho g d, and then the area of this rectangle. So it's the pressure onto this area, right? But we actually know the area, right? So we can actually write this out. Rho g d, and then it's 2 times A delta x, right? Because A was only that half of the rectangle, so its total width or its length is 2A, and then we made this guy really, really small, and we're going to call it delta x, right? So we can actually rewrite this guy one more time. Rho g, and then this d, in fact, is our xi. And then we can sub in what we found for A. This is 2 times 3 minus 3/4 xi delta x. So what we can do now is start writing out what our total force is, right? Because if we make these intervals smaller and smaller, we can actually take an integral, right? So go ahead and start writing that. We've got f equals the integral, and of course we're going to go from 0 to 4 because we need to go all the way down to the base of the triangle from the top. And then we've got 2 rho g, and I'm going to keep those as constants until the very end. And then if you bring in that x from the previous line from this guy over here, we've got 3x minus 3/4 x squared dx. So that delta x becomes our dx. Right? We can actually do out this integral 2 rho g 3/2 x squared minus 1/4 x to the third, evaluated from 0 to 4. And now we can plug in the values for x, rho, and g, and we're going to get a big number of newtons, right? That's 156,960 newtons. That's pretty impressive. So we found that we were able to take this shape and break it down in terms of these really small rectangles, find the force that's being applied to that rectangle, and then add them all up. So if there's another shape, like a semicircle or some other kind of weird thing, always start off by kind of figuring out what these rectangles areas are that you're traveling down or up, and then find the force applied to that specific rectangle, then add up all those forces. Okay, so another topic that this section goes over is center of mass. And when we're talking discrete, meaning that all the mass is in like one point, we have that mx is the sum of these masses times the yi's, so the y coordinate of this mass. And then our my's are equal to the sum of the same masses, but now with their x coordinates. Right? So now this is just discrete. If we're looking at something more continuous, meaning that the mass is spread over a region, we have to use calculus. Right? Now, before we really jump into that, we've got the center of mass in this discrete sense being, and the notation for that was with a bar over the coordinate, is my over m, and then y bar is mx over m. So we're actually going to be using this very similar kind of form when we're talking about continuous masses. Now, in the book, they talk about continuous masses. Let's draw a capital here. My is equal to the integral from a to b, rho x f of x dx, and that mx is equal to the integral from a to b of rho over 2, and then the quantity of f of x squared dx. Now, if you do have your book handy, notice that they actually write the rho outside of the integral. I think this is a terrible way of doing it, mainly because the book only talks about when rho is a constant. So this density of whatever you're looking at is a constant thing. This isn't always necessarily true. This could be, it could get denser as you go more to the right or more up, or maybe it's a really weird function of density. So this is actually the real way of writing these things. And if it is a constant, great. You get to move it out of the integral. and it becomes a lot easier. But note that if it's asking for a non-constant density, it remains within the integral, right? So that actually shows up later on when you're talking about center of mass, because if we're actually looking at what the center of mass is, again, it's the same thing as we had above. It's these guys, what we have in green. Those are the center of masses, even in continuous. It's this x bar equals my over m, and then y bar is equal to mx over m. Now, we have to write what m is in this case, the integral from a to b rho f of x dx. Right? And again, I left the rho in there just in case rho is a function of x, if it's a non-constant density. Note that in the book, it talks about how you can simplify these, and it's got 1 over the area times these integrals. That's because they take rho to be constant, they move out of the integrals, and you can cancel them. If rho is not in this lowercase m integral, the guy that we've got, let's do a highlighter, this guy, if rho can move out of that, it's going to cancel with the rows that are here, here, right? So just remember that it might be worth keeping in mind that rho should remain within those intervals if it's not a constant, right? All right, cool. So let's move on to our next page. And that brings us to our next example problem. So we've got number 3 here. So let's find the center of mass of this mass that's created by y equals x to the third and y equals square root of x. So I'm going to go ahead and plot what the region looks like, and then I'm going to give you guys a few minutes to work on the problem. Go ahead and find the center of mass of that guy. Okay, so we've got this region in pink here, and we want to find its center of mass. So the first thing we should really start to look at is this area. Because it's a constant density, we can go back to the equations in the book and not really worry about the rho inside of these integrals. So going to talk about this a, and the integral of the square root of x, which is the one on top, minus x cubed, the one on the bottom, dx. For now, for the bounds, you can see that if we set x cubed equal to x, or the square root of x, the first one that should really jump out at you is 0, right? And that's actually the lower bound here. And if you actually notice that 1 is a really nice thing for polynomials. So 1 cubed is 1, and the square root of 1 is 1. So we actually have 0 to 1 as our bounds on our integral, and we can find this pretty easily, right? 2/3 x to the 3/2 minus 1/4 x to the 4th, evaluated from 0 to 1, and this is equal to 5/12, right? So now we have to find our capital MX and our capital MY. Let's start with MX. Find as the integral from 0 to 1 of 1/2 x minus x to the 6th dx. Now remember, it's not the square of the whole thing, the square root of x minus x cubed. It's not that whole thing squared, it's each of those functions squared, right? So that's why we just have x and x to the 6th and no cross term, right? Now this is equal to 1/2 times 1/2 x squared minus 1/7 x to the 7th, evaluated from 0 to 1, and this is 5/28. So similarly, we're going to find my. This is equal to the integral 0 to 1 x times the square root of x minus x to the 3rd dx. Another pretty easy integral to solve. So that's 2/5 x to the 5/2 minus 1/5 x to the 5th. And this is evaluated from 0 to 1 again. And this gives us a value of 1/5. So now we have all the necessary values to find our x bar and y bar. So x bar is going to be 1/5 over 5/12. And this gives us a value of 12 over 25. And then y bar is equal to 5 over 28 over this 5 over 12. And that gives us a value of 3/7. So our center of mass is at the x coordinate 12 over 25 and the y coordinate 3 over 7. Right. And again, we were able to take away the this density parameter, this rho, because we have a constant density. Otherwise, you would have to find, instead of A, you would have to find the mass. And then when you were doing these mx and my's, there would also be a density term inside of those, making the problem a little bit harder. So the next big topic we're going to talk about is differential equations. So diff-EQ. This is also called an ODE, meaning an ordinary differential equation. The reason why it's called ordinary is because it has derivatives in one variable. When you guys get to Calc 3, you'll learn that there is possible to have derivatives or partial derivatives in different variables. And you'll also take a class later on ODEs, and you'll see a bunch of stuff there. So what we're really going to concentrate on is a special case of ODEs that we can use separation of variables on. So an ODE in general doesn't have to be y prime. It can actually be like y to the 7th, or the 7th derivative. But in this case, we're going to stick to first order, so just the first derivative. And typically they would look like this, a function of x and y. More importantly, we're going to be looking at a special case where we've got that y prime is equal to a function of x times a function of y. So we're actually able to separate these functions, and separation of variables is adequately named. So if we have the f of x times g of y kind of relation, then we can write y prime as dy over dx, and we can do some manipulating. If we get all of the things that are related to y on one side and all the things related to x on one side, then we might have something a little bit cleaner. So if I've got 1 over d of y dy, and then I've got f of x dx, then it looks like it's begging to be integrated, right? Because we have these dy's and dx's. So we're going to integrate 1 over gy dy. This is equal to our integral of f of x dx. And this is a way of solving this ODE, because this might spit out something in terms of y, and then we can try to solve for y. You're lucky if you're able to solve for y after integrating both sides. That's not always the case. You might have seen that on your WebAssign or some other problems, that it might not be possible to explicitly find y. You might just have to write out the whole relationship of multiple y's and their x counterparts. So let's go and do an example. That brings us to number 4 here. And we've got that y prime is equal to 2xy over 1 plus x squared. So I'm going to give you guys a few minutes, work on the problem, see what you come up with. All right, so what we can do is we can start with finding out if we can separate these guys, and luckily we can, right? Because we've got this entity, this 2x over 1 plus x squared, and we can say that that's times y, right? So we can separate these two entities. Moving these around, we can get 1 over y dy, and we can say that this is equal to 2x over 1 plus x squared dx. Now, again, it's begging to be integrated, so let's go ahead and do that. So we have the integral 1 over y dy, and this is equal to the integral 2x 1 plus x squared dx. Right? The integral on the left should look great, right? It's just a natural log. So we have the natural log of y. And the guy on the right, what we can do is set u equal to 1 plus x squared. Our du then is 2x dx, which is perfect, right? So on the right here, we're going to have the natural log of u plus c. We can sub in what u is now as 1 plus x squared. We're going to have this plus c. So now this equation is actually solvable for y. So let's go ahead and do that. If we take the exponential of both sides of this equation, we're going to get that y is equal to e to the c times 1 plus x squared. E to the c is, again, another constant, so we're just going to call that k. And then we have k times the quantity of 1 plus x squared. And you can check by taking this derivative that we indeed get the above relationship between y prime. Right? Okay. So the next big thing, and I kind of heavily emphasize this next section that we're going to kind of go over, is sequences. This is what you guys had assigned for today. And it's a pretty big section. We're going to try to get through some of it, see how we do. And it kind of ramps up from here. So once we get into sequences and you complete that, we're going to start talking about series. And in my experience, series has been a trouble spot for a lot of students taking Calc 2. So kind of be prepared, maybe try to get some extra time by reading ahead, giving yourself just maybe a little bit extra time to think about some of the things that are happening, because we're going to be talking about divergent and convergent series, as well as sequences and stuff like that. And it kind of takes some of the knowledge of what we learned with integrals and convergent and divergent. But then there's a bunch of other tests that you're going to have to know how to use. So be prepared for this section. I would have a firm understanding of what sequences are, and then when we move to series, I think you'll feel a little bit stronger. So what is a sequence? Why don't we go ahead and go to a whole new page for this? So sequences. A sequence is a set of numbers. So we're going to say A1, A2, A3, and it keeps going, right? We'll get to AN, and maybe it keeps going after that, right? And there's a pattern, right? So sometimes questions will give you the actual numbers, and you will have to try to derive what this AN term is. How does that number depend on N? right? And that's our an. So it's kind of like a function, but only for whole numbers, right? These integers, right? So another concept that is calculus related with these sequences is limits, right? What happens if this sequence just keeps going and it goes to infinity, right? Well, if it actually gets to something finite, we can write that as L, and we can define it as the limit as n goes to infinity of the generic term an. So anywhere in this sequence, n keeps getting bigger and bigger and bigger until eventually we kind of level off when we get to this n. Right? So now, why don't we start looking at some examples and doing this limit? Right? So number 5, we're going to have 3 sections for it. So A is this sequence here, 3n squared minus 1 over 10n plus 5n squared. And this goes from n equals 2 to infinity. So find out where these are going, if it's actually going anywhere. The next one is e to the 2n over n. And it goes from n equals 1 to infinity. And then the last one, c here, is -1 to the n over n. N equals 1 to infinity. So I'll give you guys a few minutes to work on these, and then we'll talk about the solutions. Okay, so let's start with A first. And then if you haven't finished B and C, don't worry. I'll give you a little bit extra time. Just kind of follow along for A. So let's start with A. And let's go ahead and start immediately by taking a limit. As n approaches infinity of this 3n squared minus 1 all over 10n plus 5n squared. So what I can do inside of the limit, write the limit again as n approaches infinity, is factor out an n squared on the top and the bottom. So this leaves me with 3 minus 1 over n squared here. And then on the bottom, I have an n squared, and then a 10 over n plus 5. Notice that these n squareds are going to cancel. And then when we apply this limit, we'll note that the 1 over n squared goes to 0, and this 10 over n goes to 0. So this limit is going to be equal to 3/5. Right? Now B, a little bit trickier, because if you'll notice, if we start taking a limit, so let's go ahead and start writing it out here. We have the limit as n approaches infinity of this e to the 2n over n. This limit looks like I want a L'Hopital, right? I've got an indeterminate form, I've got infinity over infinity, and that's perfect, except for one thing. This is a sequence. This isn't a function. So it doesn't have a derivative. But what we can do, and the book talks about this, it's called in Theorem 3 of the book in the section, we can say, so I'll have a little side note here, that if the limit as x approaches infinity of f of x is equal to L, and we have the condition that f of n is equal to a of n for the integers, then we have the same thing, the limit as n approaches infinity of an equals L. So we can find out this limit by making a function. So we define the function f of x as equal to e to the 2x over x. And now we can take this limit. So L limit as x approaches infinity. And we can L'Hopital it. So we'll just write out the original first. So now L'Hopitaling it, the derivative of the top, we get a 2 over e to 2x, and on the bottom we have a 1. So we know that this guy is approaching infinity, right? So by Theorem 3 in the book, we're able to write a function f of x that simulates this sequence, right? And then we were able to take a derivative using L'Hopital. Okay, so now for C, we're actually going to use a different theorem. Right now we've got the limit as n approaches infinity of -1 to the n over n. Well, in the book we have Theorem 6, which states that the limit as n approaches infinity of the absolute value of an equals 0, then the limit as n approaches infinity of an without the absolute values is also equal to 0. So let's hope that it's equal to 0. Right? Let's go ahead, and this guy is equal to now the limit. Well, let's back up because we don't know it's completely equal yet. So let's not have an equal sign there. We have the absolute value of -1 to the n over n. This is equal to the limit n approaches infinity. And now because it's going -1, 1, -1, 1 all over this n quantity, and we're always taking the absolute of that, it's just going to be 1 over n. And this is equal to 0. So by Theorem 6, we know that this is also equal to the limit as n approaches infinity of -1 to the n over n. And that's how we do C. So let's talk about some other characteristics of sequences, right? There's this concept of monotonic, increasing and decreasing, and then bounded above and bounded below. So let's say we've got some kind of graph here, and I've got some kind of sequence that behaves like this. right? And it levels off. It never gets higher than some value. Well, I'm going to call that value capital M. Similarly, if there's another kind of sequence that does something like this, and it never gets below something, I'm going to call that value lowercase m. And this discusses bounded above and bounded below. It never gets higher than a finite number, or it never gets lower than a finite number. And if it's both of these things, we call it bounded, just bounded. Now, monotonic is something that describes either the condition where an is always less than its next, its adjacent partner to the right in the sequence, so this an plus 1. So that means that it's always getting bigger, right? The next thing is always bigger than the last one. And if that's satisfied, then we're always increasing. Well, there's another condition. I should say this is an or. Gotta give myself some room here. Why don't we just go ahead and write or down here? Or we have that an is always greater than an plus 1. So that means that the next element is always smaller than the previous one. So it's always decreasing. If it's either one of these, then we call it monotonic. A lot of people say monotonically increasing or monotonically decreasing, to be a little bit more specific, but the definition of monotonic is it's either one of these things. It's always increasing or it's always decreasing, right? So let's go ahead and do number 6 here. We're going to classify these sequences. So A is the sequence of negative n squared from n equals 0 to infinity. B is the sequence negative 1 to the n plus 1. And this goes from n equals 1 to infinity. And then C is the sequence 2 over n squared. And this goes from n equals 5 to infinity. So describe if it's bounded below, bounded above, and if it's both bounded, and if it's monotonic, and if is it monotonically increasing, is it decreasing? Describe what these sequences are doing. Okay? I'll give you guys just a little bit, and then we'll talk about it. All right, let's talk about A. So we have this sequence, and we can note that we've got this condition. negative quantity, n plus 1 squared, right? Because as n gets bigger, we're going to have a larger and larger negative number, right? So if this holds, then we're monotonic, right? And we're decreasing, right? Now, we also can note that because it's decreasing, its first value should be the largest, right? And that means that an is bounded by 0, right? N is going to keep getting bigger and bigger and bigger. So as n goes to infinity, this goes to infinity. So we're not bounded below, but we are bounded above by 0. Right? So now for B, we're going from negative or 1 to negative 1 to 1 to negative 1. So it kind of looks like something like this. We're just going back and forth, right? And up here we have capital M, and down here we have lowercase m. So we are bounded, but we don't have monotonically increasing or decreasing because it keeps going back and forth. Now for C, we've got 2 over n squared, and then 2 over n plus 1 squared. That's the next element. And the equality sign that works in here is this. So as n gets bigger, the denominator gets bigger, meaning that the whole thing gets smaller. So again, we're monotonically decreasing. And if we kind of observe what we're looking at, because it's always decreasing, like B, or I should say, A, well, its first element is always going to be its largest. So that means that this capital M is equal to 2 over 25, since the sequence started at 5. Right? Now, we also know that as n gets larger, as this limit goes to infinity, this thing gets smaller and smaller and smaller and smaller until it goes to 0. So we can actually say that m is equal to 0. And this means that it's bounded and it's monotonically decreasing. And by a theorem in the book, this later talks about this being convergent. So that's all the examples that I have for this time in our recitation. I hope you guys learned something. If you guys have any questions or something like that, feel free to email me and Silva about a WebAssign problem that you're having trouble with, or maybe just a question in general. Otherwise, I will see you guys on Wednesday, and I will actually be hosting the office hours on Thursday. So you can also ask me questions there. All right, take care, guys.